Welcome back to this lecture series on deep learning. In this lecture, we'll briefly discuss about how the probability distribution is used in deep learning. Learning probability distribution is essential for deep learning because they provide the foundation for handling uncertainty, modeling predictions, and interpreting outputs. In deep learning, models often output probabilities rather than fixed answers, especially in tasks like image classification, speech recognition, or natural language processing. For example, softmax neural network converts raw scores into a probability distribution over classes, helping the model express confidence in each prediction. Distributions like Bernoulli, binomial, Gaussian, and Poissons are used in various parts of deep learning, from binary classifications and dropout regularization to generative modeling and even prediction. Understanding these distributions helps in selecting the right loss functions, initializing weights, modeling data, and evaluating results, making it a core concept for building accurate and reliable AI, artificial intelligence systems. We'll see one by one. First, introduction to probability in deep learning. The probability provides a mathematical approach to deal with uncertainty, which is a key challenge in deep learning applications. Rather than relying on fixed answers, models assign probabilities to different outcomes, which helps in making better decisions when the outcome is not certain. If you are taking this equation in the classification task, neural network output raw scores, that is logistics, which are converted into probabilistics using the softmax function. So it is being given by the probability of y is equal to e to the power zi divided by summation j is equal to 1 to k e to the power j, where zi is the model score for I and k is the number of classes. So in image classification, a neural network. So in this case, the equation ensures that the output values are positive and sum to 1, making them valid probability. So the sum should be equal to 1 for the valid probability. And the applications of this equation is in image classification, a neural network may analyze an image and determine there are an 85 chance in it's a cat. So if you have been given input as cat, dog, and other animal names, 85% chance it is a cat, 10% chance it is a dog, and 5% chance it is a rabbit. This not only helps the model pick the best answer, but also understand how certain it is about that answer. Next, discrete versus continuous variables in deep learning. The concept of this discrete versus continuous variable is discrete variables can take only specific values such as integers or categories like digits from 0 to 9. In contrast, continuous variables can take any real value in a given range like height, weight, or temperature, etc. And the applications of what is the applications of this continuous and discrete in deep learning is in deep learning, discrete variables are typically used for classification tasks such as identifying the type of object in an image. Continuous variables are used in regression tasks such as predicting the age of person based on an image. And the model handles these using discrete variables or modeled using a probability mass function PMF, which gives probabilities for each possible discrete outcome. Continuous variables are modeled using the probability density function PDF, which represents the likelihood of variable taking on a continuous value. Next, why probability distributions matter in deep learning. The probability distributions allow us to describe how likely various outcomes are. They help us go beyond point predictions to quantify uncertainty and variability in the output. The applications in deep learning learning or VAs. First one is variational autoencoders. In variational autoencoders, the encoder maps inputs to distribution that is usually Gaussian over latent variables instead of a fixed vector. This helps generate new data samples by sampling from that distribution. And the applications in deep learning, the Bayesian networks has been used. Bayesian neural networks assign a probability distribution to model weights instead of using the fixed values. This helps capture uncertainty in predictions and improves robustness in decision making. The another application is the classification. In classification, the output probabilities indicate how sure the model is about each class. This helps in thresholding multi-class decisions and understanding model confidence. Next, probability mass function PMF in classification. How this probability mass function is used in the classification, we'll see. A PMF gives the probability that a discrete random variables takes a specific value. It is used to represent uncertainty over discrete categories. So this is the equation. A valid PMF satisfies the condition summation I is equal to 1 to k, P of x is equal to xi is equal to 1. This ensures that the total probability over all possible outcomes adds up to 1. P of xi is equal to x is the probability of class xi. And the applications are in classification network, the softmax layer outputs values that form a PMF across the classes. Each output neuron's value represents the probability of a specific class, and the loss function is given by cross entropy loss is used to measure how close the predicted PMS is to the actual label. Here it is been given by summation of minus summation of I yi into log pi cap, where yi is the true label 1, or this value may be either 0 or 1, and pi gap is the predicted value. Okay, predicted probability for that class. Next, uniform distribution in weight initialization. Uniform distribution assumes that every number in a range is equally likely to occur. This is ideal for generating unbiased random variables. The equation is given by f of x, the probability density function PDF of a continuous uniform distribution is given by f of x equal to 1 divided by b minus a for a is less than or equal to x less than or equal to y. The applications of this equation is uniform distributions are usually to initialize neural network weights randomly to ensure that neurons do not start with the same value. This randomness allows the network to learn more effectively. And another here double this it is used for initializing neural network weights, and it is being given by u of minus root of 6 divided by nin plus n out, comma 6 divided by n in and n out. This keeps the activation from the exploiting or vanishing during the forward or backward passes, which helps in faster convergence. Means neurons starting with the same value and improving the convergence. So exploiting and vanishing during forward or backward passes, which helps in faster convergence. Next, binomial distribution and dropout. Binomial distribution and dropout. A binomial distribution describes the number of successes in n independent experiments, each with a probability P of success. The equation is given by probability of k is equal to ng, p to the power k, 1 minus p to the power n minus k. And the applications are dropout is a regularization technique where neurons are randomly turned off during training. The decisions to keep or drop a neuron follows a binomial process and effect. By keeping each neuron with a probability P, dropout forces the neural network to rely on multiple pathways and learn robust features and reduce the overfitting. So it will reduces the overfitting. Next, Bernoulli distribution for binary classification. A Bernoulli distribution models a single binary trial with the two outcomes. The outcomes are success is being given by 1 and failure is being given by 0. Probability 0 with a probability p of x is equal to 1. The equation is equal to p and x is equal to 0 means 1 minus p. And the application of this equation is in binary classification, example spam versus not spam. A target can only be 0 or 1. A Bernoulli distribution perfectly fits this type of problem. Next, activation function in the sigmoidal function. To convert logists into probabilities, the sigmoidal function is used. It is given by that is say eta of z is equal to 1 divided by 1 plus e power minus z. And the loss function, this ensures that outputs lie between 0 and 1 and suitable for this is suitable for binary classification. Next, loss function. The loss function, the binary cross entropy is given by L is equal to minus of y into log p plus 1 minus y into log 1 minus p. This loss penalizes incorrect predictions more as the confidence, that is probability, increases. Next, Poisson distribution for event prediction. The Poisson distribution models the number of events occurring in a fixed interval, assuming these events happen independently and at a constant average rate. And the equation is given by probability of k comma or lambda is equal to e to the power lambda to the power k divided by k factorial. Lambda is the expected number of this lambda is the expected number of occurrences and k is the actual number observed. And the applications are this distribution is used in count based models such as predicting how many users will visit a page or how many clicks and ad will get with the time window. It is used in the given forecasting and spiking neural networks. Next, continuous uniform distribution in data sampling. The distribution gives equal probability to all real values with a given range, making it useful when no particular value is favored. The equation is given by f of x equal to 1 by p minus a for x inclusive of a comma b. The applications of generative adversarial network GANs use uniform distribution to sample noise vectors that serves as the starting point for data generation. Next, data augmentation, random transformations such as cropping or rotating images use values drawn from uniform distributions to ensure variety in training data. Next, log normal distribution for skewed data. If the algorithm of a variables follow a normal distribution, then the variable itself follows a log normal distribution. This is common in real world data sets with a positive skew, and the equation is given by log of x, y given n of mu comma sigma square. And here it is being used in the applications are used in modeling data with a positive skew such as internet traffic, rainfall amounts or space signal energy model, and it models may predict the log of variables and exponential units to get the original scale. Next, exponential distribution for time modeling. The exponential distribution models the time between the events in a Poisson processes and is useful in modeling waiting times or durations. And the equation is given by f of x comma lambda into e to the power lambda x is greater than 0. And the applications are application used in survival analysis and even timing predictions such as time until a customer churns or time until the next request on a server. And coming into the summary, this is the summary of the distribution in the deep learning. And the Bernoulli's distribution. The distribution is the Bernoulli, the type is discrete, and classification is the binary classification, and the dropout mask is used. and it is used in the binary classification problems and dropout layers and suitable for outputs with only two possible values, either 0 or 1. And the next one is the binomial. It is the value is a discrete, and the model the number of successes over the multiple trials. It is used in the multiple trials used for regularization techniques like dropout, where neurons are randomly kept or dropped. Next, Poisson. It is a discrete type used to the model counts such as clicks or visits. It is suitable for modeling rare or frequent events over time or space. Next, uniform. The type is both either discrete or continuous, used in the weight initiation and noise sampling. Next, log normal. It is a continuous function. It models the speech used for speech traffic or natural phenomenon modeling. And the exponential, the type is the continuous. It is used for modeling the time until an event happens, such as machine failures or customer churn. Next, use of distributions in data science project. How this probability distributions are used in the data science project. It helps in understanding, recognizing the type of distribution in the data that is neither normal or skewed or count based. It is used in that case. It helps with choosing the right pre-processing steps, transformations, and visualization support. Next is the support model choice. Whether the target variable is discrete or continuous, it affects the whether to use classification, regression, or time series models. Distribution guide these decisions. Next, aids in data simulation. The probability distributions allow synthetic data generation, which is useful when the real data set is smaller or incomplete. It helps in testing the validating models. Next, improved decision making. Using probability based outputs enables better risk assessment and confidence measurement. This is useful in critical applications like finance, healthcare, and recommendation system. Next, used in generative models and uncertainty estimation. Distributions are key in models like VAs, GANs, and Bayesian networks, where the generating realistic data and quantifying uncertainty are essential goals. So, coming into the conclusion, mastering probability distribution is important for building intelligent deep learning systems. They help models handle uncertainty, make accurate predictions, and adapt to different data types, whether categorical, continuous, or even based. Applications span from image and speech recognition to recommendation system and time to even modeling. A strong foundations in these concepts empowers all the learners to design smarter, more reliable artificial intelligence solutions. Thank you for your passionate listening. Hope you enjoyed learning the topic.